I've got the honor to introduce the next speaker. He is a senior lecturer at UTS and really the person to talk to if you have any questions about the quantum internet. So please welcome everyone, Dr. Peter Rohde.
And it's already broken. Last time it didn't happen until the end of the talk. Of course, anybody can ask questions. It doesn't mean I can answer them. What I will do is answer my own questions. And they might be hypothetical ones that don't make sense. Nonetheless, what we're talking about is the quantum internet, which is certainly hypothetical. But nonetheless, it's interesting territory to explore because, in my view, this is one of the guiding forces for the field of quantum computing, which is what most of you are researching at the moment. And my interest in all of this started with, obviously, I wasn't a contributor to that satellite that you've all heard about, but you're all familiar with that result a few years ago of the Chinese team putting up a satellite that did nothing more than this. All it does is prepares this state, and that's it, which on the ground is quite easy, but in space is quite hard, especially if you want to make it intercept dishes 1,000 kilometers apart. And they've done that. They've made Bell pairs and did that for the purposes of quantum key distribution. But I think QKD is a very short-sighted view of where quantum networking is going to take us. In fact, I think it's a completely nonsensical one that we should only be pursuing for proof of principle demonstrations because it's something that we can do with a very small number of qubits, but it's not a particularly interesting thing. Nonetheless, let's start by looking at how they encode information in their satellite. They do it optically, they have photons, and they encode qubits in the polarization degree of freedom. So a horizontal can be a 0 and a vertical can be 1, and you have entanglement in that basis. And a Bell pair, as you know, is just any form of superposition of two qubits in perfect correlation like this. And from that, they did quantum key distribution. But a much more useful thing to do with entanglements spread over long distances is state teleportation, because this is how we can communicate arbitrary quantum information through channels that are very, very imperfect. So some of you will be familiar with the no cloning theorem in quantum physics. It tells us if I give you an arbitrary qubit and you don't know what it is, then you can't make multiple copies of it. And that's enforced by the laws of physics, unlike classical information where you can just look at the bit string and print out as many photocopies as you want. You can't do that with unknown quantum information. So what are we going to do when we have these long distance quantum communications links, but they're very, very lossy or they're very, very disrupted by noise? And obviously when you've got 1,000 kilometers of atmosphere and free space travel, most of the signal gets lost. So we don't want to be throwing away valuable quantum information when we can't reproduce it. So the workaround is using quantum state teleportation, where we start with an arbitrary quantum state and then a known quantum state, which is the Bell pair. And that's where, for example, that satellite could be useful. We spit out this known thing that's not subject to no cloning limitations because it's a known state and you can photocopy it. And once we successfully communicate a Bell pair, however many attempts we have to make, we just do it over and over again until it finally works. And when it does work, then using that shared entanglement, we can complete the teleportation protocol and do a joint measurement on the one side of one half of the Bell pair with the unknown qubit, communicate some purely classical information, and then on the other side, magically the qubit is transferred. And in doing so, we completely bypass using the quantum channel for our unknown qubit altogether. So I'm using red to represent quantum channels, blue to represent classical channels. The teleportation protocol, once you've got the shared entanglement, you don't have to use the quantum channel anymore. So what that means is that these Bell pairs are incredibly useful. They're a commodity, they're a resource for the future quantum networking, where we can use them to transfer arbitrary quantum information around. And because they're a known state, they're infinitely reproducible and we don't have any of these no cloning limitations. But on top of that, we can do even better things than we can do by transmitting information directly. Some of you will be familiar with entanglement purification. If I have a whole bunch of entangled pairs of low fidelity, they've got some noise on them, I can purify them together using protocols that look something like this, where, for example, here it's represented using polarizing beam splitters and optics. You can do it with CNOT gates as well if you have those at your disposal. But you take multiple noisy copies of a bell pair and you purify them down into one that's better than either of the ones that you started with. And you can repeat that as many times as you need to get an arbitrarily good quality bell pair. Once you've got it, then you can do state teleportation. So this obviously bypasses whatever the noise limitations on direct communication of qubits is. If you want to transfer an unknown qubit directly, the quality at which it arrives on the other side is going to be dictated by the channel, and you only get one attempt at it. If we can transmit as many bell pairs as we want and then purify them down into something really good, which is better than what a single use of the channel would allow, we can overcome that obstacle. So you can think of it as a little bit like the quantum analogy of the classical networking concept of load balancing, whereby you send things around through multiple routes to distribute the bandwidth and maximize utility of the network. Here we can distribute multiple bell pairs, and whichever ones arrive, we purify them down into a really, really good one and get very, very good quality transmission of quantum information. And so this leads to the notion of quantum repeater networks, where you have alternating sequences of entanglement swappers and entanglement purification. An entanglement swapper is something that looks like this, where two parties have bell pairs, and then some party in the middle comes and does a joint entangling measurement on one half of each. And then, hey presto, those two other ones that were never touched now form an entangled pair. So you could use this to build up a long-range network that can exceed the limits of line of sight. For example, if you had alternating satellites like the Chinese one, every second one was a source, every other one was a swapper, all of a sudden we can make a very, very long-range entanglement link. And by using purification, boost up the quality as much as we like. Now, another interesting observation about all this is that these bell pairs, they're all identical. They don't depend on the information that we're sending. Therefore, it doesn't matter when we receive them. As long as we had one at our disposal, we can pick it up, use it to transmit or teleport quantum information as well as we like, or as dictated by the quality of the bell pair. But it doesn't have to arrive at be distributed at the same time that we use it. You could hold it in memory if you liked. So there are no latency issues associated with entanglement distribution, aside from the fact that they'll inevitably deteriorate as you hold them in memory. So this led to a very interesting observation from a colleague of ours, Simon Devitt at UTS. Why not have a bunch of qubits in a heavily error-corrected system? In other words, a big quantum computer, pack a whole bunch of them onto a boat. We don't care about the latency, but when they arrive, we can use them as though they were transmitted spontaneously. The latency isn't an issue to us. So these whole observations completely change the dynamics of how a quantum network works compared to a classical network, because classical information inherently is subject to latency, and there is no notion of state teleportation. So, having all of these sorts of ideas in place, we know how to get entanglement around the world using swapping and purification, or putting it on the back of a boat, or whatever the case may be. The next slide that everybody usually puts up is this one. It says, now we can use this for perfect security to do BB84 encryption or one-time pad encryption. It's information theoretically secure. There's literally nothing anyone can do to break it. But any back of the envelope calculation will tell you that on a cost-benefit basis, that is really a completely unreasonable thing to do, given the costs that this infrastructure is likely to incur. So nobody is going to be using realistically a satellite to communicate at a rate of 1 secret bit per second for use in a one-time pad. Well, you're not going to be able to communicate a video call doing that. You're not going to be able to do anything practical from a cryptographic perspective. And more importantly, what they did in the Cold War is actually much cheaper. You just have an armed escort with a guy carrying some hard disks with random bits in a briefcase. It's exactly what they did between embassies in the Cold War. you use them once for a one-time pattern and you throw them away. And using this approach with hard disks in a briefcase, I can guarantee you that even if he was walking to the other side of the world, he'll get more bandwidth in terms of secret key rate than what any constellation network of the satellites that we currently have will ever be able to do. And it'll cost a fraction of the cost. So why are we interested in quantum networking, given that it makes no economic sense whatsoever to do it for the purposes of quantum key distribution? Well, there are other reasons. One of them is this one on the left, quantum enhanced telescopy. That's what Zixin here has been working on quite a bit and will be doing more work on. If you have entangled qubits, you can get higher resolution effective aperture on distributed telescopes. At the moment, we put radio telescopes on the opposite side of the wall to create an equivalent aperture the size of the Earth. You can enhance that even further if you've got entanglement rather than normal classical techniques for measuring the signals. There are all sorts of other cryptographic protocols too, like quantum anonymous broadcasting, where using a shared GHZ state, which is a generalization of the Bell pair, and you can make from multiple Bell pairs. Using that, people can broadcast a message without revealing their identity. But still, these aren't really, really ambitious things. In terms of getting the infrastructure investment that we need, it's unlikely that either of those two applications are going to justify it either. So the real use is, of course, quantum computing. And this is where the dynamics are very different to classical computing, as we'll shortly see. The main reason for difference is that in a classical computer, if you have a whole bunch of nodes, imagine you're building a supercomputer by just networking together a bunch of commodity CPUs using a classical network. Well, the total power of the distributed computer is just proportional to the number of cores you have. It doesn't matter how you're networking. The total power, however you choose to subdivide it, is just the sum of the parts. It's a linear relationship. But we know that with quantum computers, that's not the case. We know that with quantum computers, in principle, in the best case scenario, as you increase the number of qubits in a system, you can get an exponential scaling in the overall algorithmic power of what it's able to compute. And so that is actually, to me, the real motivating force behind all of this. And I'd like to explain how that works in the context of the measurement-based model for quantum computing. So for those of you not familiar with it, here we have a simple lattice graph. The vertices represent qubits, the edges represent entanglement links between them, where we just apply controlled phase gates. And this is completely equivalent to the circuit model for computation. Once you prepare a lattice state like this, you can go through in a predefined sequence, measure qubits, and it'll give you exactly the same output as a quantum circuit. So they're completely equivalent models, but this one's very useful to think about in this formalism because it naturally lets us think about things in a geometric way. So before I talk about how we use that measurement-based model, I want to show you some research we've done to guide us in the direction of where we're going with this, which is how well is this likely to work? If we were to have these graph states, these measurement-based quantum computers, and instead of being localized in a single device, we were to spread them out the way we do with data centers at the moment, how do we go about figuring out how viable that is? So this is the research that Hudson Leone here has been working on, my student, and we've really made a software package called QNet that does what's called cost vector analysis in quantum networks. Now, cost vector analysis is something that's been done in classical networks. When I send you a message over normal TCP/IP, it uses a route finding algorithm to figure out what the best way to get from one place to the next is. And for the larger part, they use variations of things like Dijkstra's shortest path algorithm or distributed versions of that to find what the most efficient way to get from one point to another is. And you can think of that in graph theoretic terms. If I consider nodes now representing different geographically separated parties, and the edges between them represent communications links, whether it be classical or quantum, if I associate a cost with an edge, which is by some arbitrary measure how expensive is it for me to utilize that channel to get data from here to there, then to get a full path through the route, I just add up the costs of the edges if they're additive. So if we're thinking in dollar terms, for example, AT&T said you have to pay me $1 to use that channel, and then T-Mobile said you have to pay me another $1 to use that channel, but it needn't be dollars, it could be bandwidth allocation or whatever. Then we can just call the shortest path algorithm and say, which route gives me the smallest sum of paths to get from one place to the other? So this is exactly what our normal classical internet does. We wanted to think about this in the quantum context, where we're measuring completely different things. And in particular, in quantum channels, we want to look at what types of quantum processes will be, the qubits will be subject to, and how do we make that compatible with this kind of formalism. So I'll give you a few examples of well-known quantum channels that we can use to reconcile with this. So consider a lost channel. With some probability, you do nothing to a state. With some other probability, you throw it away and replace it with a vacuum state. Your photon gets lost or your qubit gets lost. You could consider a depolarizing channel where with some probability you do nothing to the state. Otherwise, you replace it with a completely mixed state and you've destroyed all your quantum information, but the qubit is still there. Or you can have a dephasing channel where with some probability you do a phase flip on the qubit. How do we make those sorts of channels compatible with this root finding cost vector approach that we're adopting from classical techniques? Well, these probabilities are multiplicative. If I have a bunch of these channels one after another, those probabilities start multiplying together. We want to make them additive. So obviously, how do you make something that's multiplicative become additive? You put it into logarithmic form. So if it's a lost channel, well, people in experimental quantum optics do that all the time. They talk about decibels per meter in terms of loss. And then it is an additive metric. It's just decibels per meter times the number of meters is your total decibelic loss because it's in logarithmic form. You could do exactly the same with a depolarizing channel like this. With a dephasing channel, we have to modify it a bit. Because if you apply multiple phase flips, it goes back and forth. It doesn't steadily deteriorate, it just oscillates. So we want to get it into a form where it's asymptotically approaching a steady state. And the steady state of the dephasing channel is the completely dephased state. So the general recipe for all of these channels that we've got here is you group things together into a component which is unaffected and a component which is sort of the steady state of a channel. So for a depolarizing channel, the steady state is the completely mixed state. For a lost channel, the steady state is the vacuum state. For a dephasing channel, the steady state is the completely dephased state. And you could do the same for any sort of quantum process that can be thought about that way. And then we can also then just take the logarithmic form, and we've got a way of looking at how dephasing or depolarizing or general Pauli channels accumulate as we propagate through these routes. So this is actually an output from Hudson's software showing how this route finding works for 3 different users color-coded here, where we're using what's called multipath routing. So in the classical case, we always just want to get a block of data from here to there the quickest way or the cheapest way, and that's it. But in the quantum case, we know that we're not transmitting the data directly. We're transmitting these bell pairs. They're all identical. And we have the observation that if we have multiple copies, we can make something better than any of the individual ones. So this leads away from shortest path routing to multipath routing, whereby we don't just take the shortest path, we might take a bunch of non-intersecting or distinct shortest paths that we selectively take away up to some threshold. And then at the end, we purify them all together. So here we've got 3 different paths for each color. They all get purified at the end, and they give us something much better than if I was to just take the shortest path between one point and the next. Right, so this was my recipe. We decompose an arbitrary channel that you can think of into a good part and the steady state junk part, but it also applies natively to anything that is additive, like monetary cost. So this is the paper that Hudson has written. coming out shortly. This is just one result from his paper. I'm not going to steal his thunder because Hudson will no doubt be giving a talk on this very soon. But here's an example of what our QNet package is able to simulate. Here we've passed it a grid network and said, let's consider two different types of costs in our cost vector. One is dephasing channels and the other one is loss channels. And there's a trade-off between those two. They don't just work monotonically with one another. So here we get a contour plot showing the regions where you get different fidelity versus efficiency trade-offs for randomly chosen users in our network. Now, superimposed with these blue-colored ones, those lines show us when you combine the fidelity and the efficiency for a given point, what's the effective secret key rate? So we're going back to QKD, which I discredited it as nonsense, but I'm going to use it anyway because it's simple. So here it's telling us that in this regime down here, per time step, we're getting 0.01 secret key bits per step, and then those different contours give us different amounts. So from our package, we can directly read off and see exactly what the network performance is like for this particular application, but you could define the application differently. If you're doing distributed quantum computing, you're not interested in the trade-off between fidelity and efficiency so much using the same formula, but rather you want to keep them within whatever the fault tolerance requirements of your computation are, depending upon how you're encoding things. So now coming back to where does this lead us for the quantum internet? We've discussed how we can go about estimating how these networks perform using these cost vector approaches. How do we actually go about physically building this infrastructure? Well, so thinking about the measurement-based model that I described before, imagine we've got 4 different hosts in different places around the world, and they've all got a little lattice cluster, graph state, that they can do small computations on. And we can make the observation that if I want to do a bigger computation involving more qubits, if I were able to join those together in like a patchwork, I'd be able to make a computation that is bigger and far more powerful than the sum of the parts. This one big computation involving all of these qubits is a much more powerful one than doing 4 in parallel that are each 1/4 of the size. So how do we go about fusing together these disjoint quantum nodes that might be in different places on the Earth? Well, the obvious way to do it is using entanglement distribution, because a bell pair is identically equivalent to a 2-qubit graph state. So down in this diagram down here, these blue lines, they represent our entanglement distribution. They give us exactly 2-qubit graph states. Then we have our nodes with our little clusters. We can perform local controlled phase gates on each side to join them together. And that creates a distributed graph state equivalent to this topology down here. And we can do that, of course, in the upward direction and as much as we like to build up arbitrarily complex distributed topologies. So why do we want to do that? Well, the reason is, in the classical case, as mentioned, you get something necessarily as powerful as the sum of the parts, but in the quantum case, that's not the case. If you consider something like this, where we've got the best case imaginable algorithm that has exponential classical equivalent performance, scaling with the number of qubits, if I was to do the classical approach of just everybody gets allocated a small computational problem and then we reconcile it at the end, you'd get the sum of these exponentials. But by unifying them into a single bigger computer, we shift that sum into the exponential. And so you can immediately see that if we have a whole bunch of distinct quantum computers, if there is infrastructure in place to allow them to unify and unite their computational capabilities, we're going to necessarily get something much better than what we started with. But that, of course, raises security questions. If I'm going to be outsourcing a computation to this big worldwide distributed network, some parts of it in that country, some in that country, all with our own spy agencies, some have Zuckerberg, others have whatever dictator, we don't trust any of them, we've got the usual problem of security. Well, in the quantum case, we can do something called homomorphic encryption, whereby when we outsource a computation, we can have information theoretic security in ensuring that the person doing the computation is not able to know what the result of the computation is. And this is something that is not practical when we do classical computations. When you outsource something to the cloud here, there is simply no way to do that. You have to have trust in the provider. And in most cases, that's highly questionable, as we know. What if we could be absolutely certain that when we outsource a computation, we can know by the laws of physics that they're able to do the computation for us and provide the answer to us without knowing what it is? That's what homomorphic encryption is, or blind quantum computing, a slight variant. I'm going to skip this implementation to go to this hand-drawn one. So those of you familiar with some of the details of Clifford circuits, people familiar with Clifford circuits? This is a class of quantum computations which they have all the usual features, huge amount of entanglement, as many qubits as you want. However, and an exponential number of terms, but they can be efficiently classically simulated. And these circuits are comprised of a subset of gates, which are called the Clifford gates. It includes things like controlled knot and controlled phase and Pauli gates and Hadamard's, all the usual things, except for one, which is the T gate, which is a single qubit gate that does a 1 qubit rotation at a specific angle. If you don't have the gate in there, it's classically simulatable. If it is in there, it becomes quantum universal, and all of a sudden you get all this computational power. So we're going to focus on Clifford circuits, which are easy to simulate classically, but they have the property that if you have Pauli operators, so single qubit Pauli rotations at the input of the circuit, they can be commuted through the circuit, the Clifford circuit, to give you the same circuit with a different combination of Paulis at the output. And importantly, it's very classically efficient to figure out what that commutation relationship is. So imagine we've got a Clifford circuit, which is not computationally powerful, but we're going to use it anyway. We're going to precede it with, on every qubit feeding into the circuit, random Pauli rotations. So with 1/4 probability, we choose I, X, Y, or Z on each qubit. That is the equivalent of putting each qubit through a perfect depolarizing channel. So there's no quantum information left at this point here, assuming that you don't know which I, X, Y, or Z was chosen. Okay, so if that's known to you, it's not a depolarizing channel. You can just reverse it. If it's not known to you, it's the equivalent of a depolarizing channel. Okay, third disaster. So what we have is a situation where, imagine Alice is on this side. She's preparing a state that she wants computed on her Clifford circuit. She doesn't want Bob, who's the server with the computer, to be able to know what's going on. So what she does is she applies the depolarizing channels to every qubit by flipping a coin and choosing I, X, Y, or Z for every qubit. She knows how to undo it at the end because that can be easily calculated. But Bob just sees this completely mixed nonsense. It isn't able to extract any information. So we can use that for homomorphic encryption. But the problem is that, as I said, this is all a circuit that you wouldn't want to outsource anyway because it can easily be classically simulated. Clifford circuit's not interesting. We need the T gates in there. But the T gates don't have the property that the Pauli gates can just be commuted through them anymore. So we use a slight trick, which is this idea of magic states that a lot of people working in fault tolerance will be familiar with. Instead of doing a T gate, you can prepare a state called a magic state, which when you complete a gate teleportation protocol, it has the equivalent of effect of a T gate within the circuit, but you converted it all to a state preparation stage at the start. So the only change we need to do to make this model here universal for quantum computing, therefore interesting again, is have a bunch of extra ancillary qubits at the start, which are magic states. And then everything within the computation itself is all Clifford stuff. You can commute through your depolarizing channels and undo them at the end, and Bob will have no idea what the computation was. So these are possibilities that don't exist classically. And then we have a secure model for distributed quantum computing in the cloud, where the cloud is not one single provider, but could be potentially all of them unified together. So let's think about the logic behind this unification of resources more. Suppose for a given application, I've got some function here, this FSC, the scaling function, which tells us for a given number of qubits in my system, what's the equivalent classical power of it? So imagine you're doing Shor's algorithm. That relationship would be, you know, something exponential, assuming everything was done right, whereby the classical equivalent runtime of what you're doing with some number of qubits is an exponential relationship. For classical computers, this is always a linear function. And in quantum computers, in the best case, it's an exponential function. So imagine now that we've united all of the world's quantum computers into one big one. Then the question is, well, we know that it's best if a single user uses all of it at once rather than distributing it, like chopping it up. Otherwise, we defeat the purpose. So how do we schedule this? Well, you allocate people timeshares the way you do on supercomputers. But the goal here isn't to give people part of the computer. You want to give people access to the whole computer for whatever time they need. So if we allocate people time on this unified computer proportional to what they contribute, so there are 100 qubits in the cloud, I contribute 10 of the qubits to that unified resource, therefore I get to use 10% of the time. That's a perfectly fair way of allocating that. So we'll call R the ratio that a given user contributes, and therefore the ratio of the timeshare that they get. And then you multiply that by the equivalent classical power, and you get their timeshare contribution of the power. And if you compare that with what they would have got by using all of their own resources all of the time without time sharing, you get this multiplier which tells us how much extra computational power they get for free by being a part of that system as opposed to going it alone. And that ratio, that leverage ratio, directly reflects the scaling of that scaling function at the beginning. So if you've got an algorithm that has an exponential scaling relationship, you'll do exponentially better by uniting your resources with everybody else's and taking the proportionate timeshare rather than going it alone. So from that, what are our observations about what we should be doing and what our motivations are? In the classical case, we have all of this cloud infrastructure everywhere. What are the reasons we do it, even though there is no leverage like this because it's all linear? Well, we do it primarily as a portfolio management exercise in risk management. You don't want all of your data centers in one place because it makes it at higher risk. If something goes wrong, it all gets destroyed. So we distribute it all around the world. Otherwise, we just put it all in Antarctica where the cooling is free. We don't do that because then it only takes one nutcase to walk in with a bomb and destroy the whole thing. So we distribute everything around the world. That's why we do it classically, but there's no actual computational gain. And also by doing it classically in the cloud, we also maximize efficiency and utility. It isn't viable to have a Google database in my physical phone. My phone acts as an interface to doing it centrally, and it's much more efficient that way. So in the classical case, the scaling, this ratio is just linear. In the quantum case, all of these normal arguments still apply. We diversify risk, minimizing the risk of geopolitical tension and information being destroyed in warfare and all the usual arguments. But we have this collective effect whereby if we unite our resources, we all do better than we would do individually. And that changes the strategic dynamics completely. So imagine a hypothetical scenario where there are just two world superpowers and a bunch of lesser powers, which basically sums up the situation. So imagine those two superpowers had roughly parity with one another. They dominated the quantum computing sector. They had roughly the same amount of it each. What are they incentivized to do? They're going to be incentivized to put up as many of those satellites as possible to unify them together. And then both parties will each have far more power at their disposal than if they didn't use that entanglement to unify their computations. But what happens if one if there was no parity and one was left behind, and they were acting more as a client state. In Australia, that's what we do. We're a client state of regular cloud quantum computing. All of the cloud infrastructure, primarily overseas, certainly all foreign owned, and we're a client. What happens if we're in that situation with the quantum infrastructure? Well, it's still the case that you get all this benefit by being part of this unified network. The disadvantage comes when things get adversarial. If you have a small number of qubits that you're contributing to the huge network and you're acting primarily as a client, if they cut you off, then you're not just losing access to their resources, you're losing access to the exponential scaling associated from having the sum of the parts in the exponent. So that can be used for gunboat diplomacy. So if you imagine a situation like this now, where a Russian hacker has no direct access to quantum technology, delegated a factorization algorithm to the cloud, blah, 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 blah. Turns out that it's Edward Snowden. He can do this on his adversary's own hardware. Licensing it out is completely secure from homomorphic encryption, and they wouldn't know. That kind of situation is completely viable in the quantum world with homomorphic encryption and distributed cloud. So why wouldn't you want to be part of that cloud? Well, to prevent that kind of minor adversary getting all of this exponential power for free via these leverage effects. And of course, then Donald Trump comes out and says the fake news, thinks the Russians are using our quantum internet, the best quantum internet against us. I would never allow this out. I actually put this in our book that is coming out shortly. And then the editor wrote back at one point and said, I'm worried about getting sued. We don't want to get a call from Rudy Giuliani. Can you change the picture? So I said, sure. And then I changed it to that one. And then it was all going fine. And then on the day of the Capitol riots, the editor wrote back to me and said, can we please just remove the Trump tweet altogether? I said, yeah, sure. So unfortunately, neither of these are appearing in the book. However, getting back to geostrategic politics, tweets aside, we can directly quantify what that asymmetry is between geostrategic adversaries. We know how much gain via these leverage factors people get by joining the network, but it's different depending on who you are. If you're a smaller player, you gain relatively far more from unifying with the network and taking a timeshare than the larger powered player does. So that means that the minor parties disproportionately benefit from this, but at the same time, they can also be disproportionately leveraged so should the larger powers decide to turn against them. And so the idea of quantum sanctions will be far more effective against minor quantum players than larger quantum players, unlike what we see in the classical world. And already this is a huge problem in the classical world when we see sanctions coming in and disrupting the flow of technology between borders. In a situation where we have a collective benefit, potentially to an exponential scale from unifying our assets, if you're the smaller player and the one who disproportionately loses that exponential game, should the larger player say, do what we tell you to do, otherwise we'll cut you off from the network, that could be one of the most powerful diplomatic tools in the future when this technology exists. The way to minimize that effect is by parties not being client states, but trying to ensure parity. Now, in the Cold War, they did this with nuclear bombs, and it's not great to have everybody to have as many nuclear bombs as one another. But this is different because this is technology that ultimately drives humans forward rather than blows us all up. So I wouldn't call it mutually assured destruction. I would call it mutually assured benefit and mutually assured destruction if you stop doing it as opposed to if you keep doing it. So putting all that together, this is the cover of the book, actually, with the cartoon I drew of all of the sensible and not so sensible things that are a part of this quantum internet. But really, I'm only interested in the quantum computing because I just don't think there's a lot of sense in sending boats around full of qubits when boats full of armed men with briefcases is much cheaper for the purposes of key distribution. And as a result of these QNet simulations we're doing, the ultimate goal of all of this is to put all of this together in a big picture and understand what are the economic sensibilities in rolling this infrastructure out. It's certainly not going to be for QKD, but if we do have remote quantum computers, understanding the point at which it makes economic sense to unify them together using entanglement distribution networks, that is an absolutely essential question to answer, because there is going to be a point where what you gain from linking them together provides so much more return on investment than just building more computers. Okay, so if you've got two massive quantum data centers and it's relatively cheap to build an entanglement link between them, that'll probably give you far more computational return than using the same amount of money to build more data centers. And that's the question that we're trying to ask here, is what is the way forward in laying out this technology? Because at the moment, the motivation isn't clear. The Chinese quantum satellite is a fantastic proof of principle experiment, but I can guarantee you that no one is going to be using it for secure phone calls. So I referred to the book. This is it, with Cambridge University Press, coming out soon. We've got contributions in there from Zixin, a new Macquarie SQA member, Simon Devitt, who's at UTS. This is coming out soon. I can give you advanced copies